Hello, Stat Nation. This is chapter 5, day 6. We're doing probability. And as I have said in previous videos, probability is the single most requested thing for me to go over and over with kids. So with students. So it's not easy to do. So I'm making quite a few videos on this. You're going to want to stop constantly and pause the video and write the notes down and all that kind of stuff. So let me share my screen and we'll get started. Okay. Move my picture over here so you can see me. Not that you want to do that, but there you go. All right. So we've done this quite a bit. We're doing conditional ability, and that means if or given that. That line is basically a fraction bar, as you can see here. Okay. If or given that. All right. So question 1A. Cards are randomly drawn from a standard deck of 52. Find the probability that one card is a 9. Given it's red, no problem. We know there are 26 reds. This is a pretty easy problem. Okay, and there's 2 of them that would be 9 and red. So that's the intersection of those, okay? So if you think that makes perfect sense, about 0.0769. That formula here is in the background, but doesn't really come into play a whole lot. But if you think about it, the probability of A, which is just, it's 26 of them here, right? But the probability of A intersection B, what's the intersection of red and 9? Because we know that there are 4 reds, but there's only 4 9s. There's only 2 of them that are red. Okay, that's the logic on that. You don't know what this formula is, just kind of running in the background. Isn't always needed. Sometimes it is, but we may not get to those quite today. All right, one card is a spade given it's black. All right, this is how you write it out. Then, of course, there are 26 black cards and 13 of them are spades. Okay, one card is black given it's a spade. And then in this case, that's going to be all of them because every single spade is also black. Okay, let me slide this up just a little bit now. The third card drawn, 3 cards are drawn. The third card is the first black. Okay, you're into your non-replacement. So this means we got a red card right away. This means we got a second red card. And finally, we get a black. There's still 26 of them left, but there's 2 less cards. Multiply all that together because they're independent events, and it's about 13%. Okay. The next one, 3 cards are drawn with no aces. There are 4 aces. So there are 48 non-aces. Pretty good chance on draw number 1 of not getting an ace. Draw number 2 is a little less likely, not much. Draw number 3 is a little less likely, not much. Multiply them all together, and it's almost 80%, which makes sense. If you're going to draw 3 cards, you don't get any aces very often. All right, next one. At least one. Oh, we have hammered on this in previous lessons. At least one. And again, at least one is 1 minus none. 1 minus none. Okay, so we got to calculate the probability of getting no clubs. There is a good chance of that. Okay, no clubs, or a decent chance, I guess. So the first draw, it's a 3/4 chance of not getting a club. That's 39 out of 52. The second draw is a little less common, 38 out of 51. And the third is 37 out of 50. Awesome. So we're going to multiply all that together, and that's going to give us a 41% chance of not getting a club. So at least one literally means you could get 1 club, you could get 2 clubs, or you could get 3 clubs. And it's kind of hard to do all the math on getting 1 or 2 or 3 and adding them all up. So the quickest way is to go 1 minus don't get any of them. And that'll leave you with the summation of getting 1 or 2 or 3 all together. Okay? That's a common problem. I would star that baby. Very common problem in the AP world to some level. Okay. Next set. Let me slide up. An Easter egg hunt has 8 eggs with candies, 10 eggs with toys, and five empty eggs. Oh, empty eggs, that's sad. So there are 23 total eggs. Okay, there's 23 of them. Okay. Find the probability that you find one egg with a toy. One egg with a toy. That's 1023. That's easy. The first 3 eggs all have toys. All right, non-replacement. I'm assuming you don't put the thing back. So there's your countdown again. That's just like the previous problems to the left. There's your countdown. You can kind of figure that one out by yourself. Okay. The first 3 eggs all have toys. The next one is the complement of this. It's the complement. The first 3 eggs are not all toys. Oh, well, if this is all 3 are toys, then not all toys would be 1 minus that particular decimal. Okay. All right. Item 4. The 5th egg found is the first empty one. The 5th egg, let me slide this down a little bit. The 5th egg found is the first empty one. Okay. So the empty ones, there are 18 non-empty ones. If you get one of those, then there are 17 non-empty ones, then 16, then 15, and then you finally get one of the 5 empty ones, but there's only 19 remaining at that point. Again, classic non-replacement problem. Multiply all that together, about 9%. So there's, if you draw 5 eggs, there's only a 9% chance that that's the first one you'll get is in the 5th try. Okay. All right. Question V here, 5, I guess. You have 4 eggs to find your first candy. Okay. Now there are 8 candies. All right. So here we go. So there's 15 non-candies. Then there's 14 non-candies. Then 13 non-candies. And finally, with only 20 left, you get one of the 8 non-candies. You multiply it all together because they are theoretically independent problems. Okay. All right, here's your at least one problem, at least one. Again, 1 minus none, okay? At least one means you could get 1 egg with the candy, or 2 eggs with the candy, or 3 eggs with the candy, or 4 eggs with the candy, okay? At least one. Okay, so I'm gonna go 1 minus none. What are the chances I don't get any candies? Okay, so there's 8 candies, so there's 15 non-candies, then 14, then 13, then 12. Multiply all that together and I get about 15%. Then I go 1 minus that, and that gives me the chances of getting at least one of the first 4 eggs as a candy. Okay? All right, at least one of the first 4. All right, next one. Next one. This is a cool problem. This is a table, okay? Tables are really great because you can really see the conditional probability really well in a table. Okay, so these numbers, I'm going to write them a little better here. I apologize for where they're written on this, but it's okay. So I'm going to go 14, 13. This is the table totals. 10, 7, 44, 21, 11, and 12. Okay? Find the probability of randomly selecting a person in high school or has a pet. Awesome. In high school or has a pet. All right, remember these OR problems. OR means to add. Okay? OR means to add. I'm going to go ahead and do this. In high school. In high school is right here. So that's 11 of the 44. Or has 1 pet. 1 pet's right here. That is 13 of the 44. We have to subtract the overlap. Remember that. Subtract the overlap. Again, I'm going to write the equation here. Probability of A plus probability of B minus the probability of the intersection. That upside down U right there is intersection of A and B, okay? And that intersection, let me change colors. That intersection is seen right there, that 2. You can see it physically. We double counted the 2. the kids that are in high school and have one pet, okay? And of course, that ends up being 0.5. I have the answer right there. Okay? Got a lot to erase here. So let me try to erase this as efficiently as possible. Okay, get rid of that. I want to keep my margins. Okay, got it. Okay, now, in elementary and has two pets. Oh, this is easy. In elementary and has two pets. There we go. That's 6 out of 44. Okay. In elementary and has two pets. That's easy. Okay. In college or has 0 pets. The next one. In college or has 0 pets. Okay. In college or has 0 pets. Great. In college, right here. In college, that is, let me move it up here a little bit. That is 12 of the 44, right? Or means plus, has 0 pets. There's the 0 pets. That is 14 out of 44. But I got to subtract that overlap. And you can see that's 7 right there. There's my arrow. That 7 is the overlap. Okay? And that ends up being 0.4318. Don't want to double count the kids that are in college and have 0 pets. Don't double count that and part, okay? Now, and means multiply if the events are independent. These events in this table are probably not independent. I would think college kids have fewer pets because it's inconvenient. Okay, so they're not independent events. So we have to look for the number instead of multiplying to get it, just so you know. And that's a difference between A and B, which are assumed independent events, and C from a table, not assumed independent events. Okay? All kinds of little things that can make students or learners of this very confused. And it's not easy to do. I totally get it. All right, next one. Again, this problem is pretty easy. Has 0 pets given they're in college, all right? Has 0 pets given they're in college. All right, college kids are right here, okay? So there's 12 of them, and 7 of them have 0 pets. Pretty good chance. If you're in college, pretty good chance you're not having a pet. And I'm going to slip this one in before I go to the last one. Is in college given they have 0 pets. That's different. Let me change colors on that so you can see this differently. Is in college given they have 0 pets. Given they have 0 pets, what are the chances they're in college? 7 out of 14 or 1/2. Okay, so let me slide down to the last question, or last 2, I guess. Now, like it is one. And I'm going to make this a little bit smaller so you can see it. Okay. All right. Has at least 1 pet given they're in high school. Has at least 1 pet given they're in high school. No problem. Given they're in high school is right here. Okay. And has at least 1 pet. Aha. We know at least 1 is 1 minus none. But we could do it the other way too. No problem. At least 1 is 1 or 2 or 3. And if you add those numbers up and divide by the marginal total, which is out here 11, you'll get about 64%. Okay, so that's a good couple nice little prompts there. Prompt 2 is just tremendous. I absolutely love this prompt. I just think it's the greatest. Okay, this is a fun prompt. It's one of the greatest ways to learn probability is through a table like this. You're going to love this, okay? So we're going to focus eventually on question J and K. J and K are the ones that are a little tougher and they do need me to take my time on that. They're not easy to do, okay, but they're really great. All right, the Titanic. Most everybody understands the Titanic. They've seen the movie, they've bought the CD, they know the music, okay? We know that there were a lot of males on the Titanic ship. We know that, okay? In fact, there were 1,700 males on that boat and 470 females. Wow. That's a lot. That's, it's 5 times as many, or 4 times as many, I should say, males and females. If you remember from the movie, which is my only reference, a lot of the single guys were in the hull on the bottom, including Leonardo DiCaprio. And they were either, on a fun trip to America, or maybe just, coming to America permanently. I don't know, all that stuff, okay? And we also know from the story that gender and survival were not independent variables. We know that women had a lot better chance of surviving given the culture of the day, where it was women and children first in an emergency. So we know the answer to this question that I'm circling. Are gender and survival independent? No, we know that, okay, because we saw the movie, we know the story, but we're going to prove this mathematically, okay? And it's not even close to being independent. So, which is what makes it such a good prompt. Okay, so question A, suppose you were randomly selected a name from the Titanic's passenger list. What are the chances they survived? No problem. Survived would be 711 over 2201, right there. That's the numerator. That is the denominator. Okay, no problem. B, what are the chances they were male? Male, lots of males, 1731 over 2201. Fantastic. Okay. C, what are the chances they were female and survived? Female and survived. Well, and means multiply if they're independent events. But these weren't, you already know. Plus, there's a table to actually get the right answer. That's 344, female and survived, meets both qualities. It's two-way table, female and survived, two-way table, 344 over 2201. You see the answer right there, okay? All right, and then I made a note that they were independent, so you can't multiply them, okay? This right here, female and survived, is going to be a key thing we're going to use to answer item J, female and survived, which is going to be great, okay? So keep this number in mind as we go down the line. We know the answer to this. Female and survived was a 16% chance. Now, if they were independent, it would have been a different number, and we're going to talk about that in item J. Okay, it's going to be great. Okay, now, male or died. Remember, or means to add, but be careful of the overlap. So here we go again. Probability of male plus the probability of dying minus the intersection of male and dying. Remember this, dying, that's a D. This means intersection, the upside down U, okay? So graphically, probability of being male, probability of dying. You can see the overlap is 1364. So male or died is literally this problem, 1731 over 2201 plus 1490, which is right there, over 2201 minus that intersection, 1364 over 2201. Yeah, there's other ways to do it, but that's the mathematical, technical way to do it, okay? So there's that problem again. An or problem means you got to add them up and subtract the overlap. If the overlap is 0, then the events are mutually exclusive and cannot happen at the same time. If the overlap is the product of those two, the events are independent. And if the overlap is a given number, like it is here, then the events are not independent and they are not mutually exclusive. Okay? Pretty cool. Pretty hard, though. It's pretty hard to grasp that. It takes time. All right, item E. Okay, these aren't too hard. These last few here, these last 5, not hard at all. Okay, they are all conditional probability. The conditions are changing. We're not talking about 2201 anymore. We're talking about just a condition. Probability of survived given that you're female. Okay, here is the female given that you're female. There's the survived given that you're female. Real good chance. 73% chance. Okay, I'm going to bring this up later as well when I do a really good explanation of this question. I'm going to really go into this question for many, many minutes. Okay, very cool. Okay, probability being of male given that you survived. Of male given that you survived. Given that you survived, what are the chances you were male? It's kind of interesting that over half the survivors were males. But there were so many more males. Look at that. That, you know, the ones that survived, it made it look like it was maybe fair at the end or whatever, however you want to look at it, but it wasn't. Okay. All right. Died given that you're female. Given that you're female, what are the chances that you died? There it is again, 126 over 470, no problem. Male, given that you died. Given that you died right here. What are the chances that you were male? That's 1360. Look at that. 91% of the dead were males. Holy smokers. 92%. That's amazing. Okay. And then female, given that you survived. Female, given that you survived, a little under half. Okay. That's actually the complement of this one, by the way. 1 minus that. Okay. The next one, are gender and survival independent? This is going to take me some time. So settle in. I'm going to try to go as slow as I can. This is an important question, and it is asked very often on the AP test. And there's 3 ways to answer the question. You can answer it with looking at the multiplication of independent events, which is what we're going to do. So the 3 ways to answer this question are: 1, looking at the product of independent events. Independent event. Product, this is of, product of independent events. 2, you can do a chi-square test. A chi-square test, I believe, is chapter 11. I won't touch it here. And 3, you could do a 2 proportion test. 2 prop Z test. I'm going to touch on that today, but that's in a later chapter as well. I forget which chapter. Okay. So let's first look at data that is completely independent. I have fictitious data that I made up, and it's going to help you understand this. So I'm going to start with data that's totally independent. Okay. So politics is always interesting. And I find gender and politics really interesting. Republicans, that's Rep, and Democrats, that's Dem. Males is M, females is F. And let's say I sampled 45 people in my stats class. And let's say there were only 15 males and there were 30 females in that class. No problem. So of the 15 males, 10 were Republicans, 5 were Democrats. By the way, I'm an independent, so these are just numbers to me. Don't worry about it, okay? And the females are 20 and 10, and then I make my totals. And the question becomes, is there a difference? Are gender and political party independent events? Are gender and political party independent events? Okay. Using common sense, let's just make 2 proportions. I'm going to circle this down here. Let's just make 2 proportions. And let's look at Republicans. For the males, 10 of the 15 were Republicans. You can see that right here, 10 of the 15. 20 of the 30 females were Republicans. Are those ratios equal? They are totally equal. They are both 2/3 or 0.67. So common sense would tell you that these two variables are completely independent because the males and the females are signing up to be Republicans and Democrats at the exact same rate. So if the rates are the same, then the events are deemed independent. Or if the rates are close to being the same, then the variables are considered independent. Okay, these are exactly the same, so I don't have any wiggle room. Okay, so it looks like in this table, the question of are Republicans and Democrats, political party, and gender are the independent events? Yes, they are, because they are signing up for the parties at the exact same rate. Awesome. Okay. Now, one way you could look at it is you could ask the question, what is the probability of being a female and a Republican? Female and Republican. Here we go. Okay. So you could do male and Republican, male and Democrat, female and Democrat. There's 4 ways to do this. So female and Republican. Okay. And you can see, let me redraw that for a second here. I hit the erase function by accident. Okay. Don't do that, kids. Don't hit the erase function by accident. Okay, so female and Republican, that's going to be 20/45. We know there's a 20/45th chance, and by the way, that is 0.44. We know, I'm doing this down there, by the way. We know that there's a 20/45 chance of being a female and Republican. If they're independent, then I should be able to multiply the chances of being female in this class, 30/45, and Republican, which is also 30/45. And it should give me the same answer. And if you break your calculators out, it does. So that's an example from fictitious data, how the 2 proportion test and the multiplying to check for independent events is related. Now let's try this from the table. This is going to be great, okay? And again, I'm going to go nice and slow here. Okay, so let's look at this and ask the question, what is the probability of being, how about female and surviving? By the way, female and survived, we actually did this already. Female and survived, okay, right there. So we know the chances of being female and surviving is 344 out of 2201. We know the answer to that, and that is 0.1563. Now, let's look at this from the perspective of being a female and surviving, doing the multiplying. What are the chances of being female? 470 over 2201, okay? 470 over 2201. 470 over 2201. And surviving. Surviving is 711 over 2201. If you multiply those together, you're going to get 0.069. I have a small explanation right here, by the way. Okay. Now, let's look at these numbers. This is incredible, okay, to see how much of a difference it was. I changed colors there. Look at that. If the events were independent, if they were independent, then you could multiply and you could say, if they're independent, the chances of being female and surviving is around 7%. But we know it wasn't. The chances were actually around 16%. That is almost double, probably is around double. That's amazing, okay? So you doubled your chances of surviving if you were a female in this particular situation. And that shows you that these events were not independent. Okay? That explanation right here. If you showed this work for this question and you put the word no, they weren't independent, and showed these numbers, you would get full credit. You would be demonstrating that you understand the math does not add up. They don't equal each other. The probability of being female and surviving was much higher than it would have been if you multiplied it out if they were independent events. Now, let's look at this to show you this from the two proportion perspective. Okay, from the two proportion perspective. All right, the chances of being, if you were male, what are the chances you survived? 367 over 1731. Wow. 367 over 1731. I think I did the math ahead of time. Maybe I didn't. 367 over 1731. I'll do that real quick. Is 0.21. Close enough. 0.21. For the females, if you were a female, what are the chances of surviving? Wow. 344 over 470. That comes out 0.73. 0.73. Look at those two numbers. I mean, they are nowhere near each other, these two numbers. They are not equal at all. In fact, they're not even close. If they were close, like they were both like 0.21 right around there, you could say, well, it was more or less independent. But this is shocking how different it is. That's the female survival rates, you know, that is 3.5 times the males. Okay. So that is not explainable by chance, meaning that these two variables, survival and gender, are not independent. Okay. That is a question you're going to have to deal with, and we will be seeing this more than just this time. I hope that's a real thorough explanation of Jay. That's a lot of explaining, but it's a fantastic question. Okay, the last one, I'm going to go to, I'll show you the answer here. Let me slide this thing down here. It is our, which classic setup, and again, it's a little cut off here, but here it is right here. Okay, circle that. Gender and survival are, okay, and there's 4 options: independent and mutually exclusive. So you have A, B, C, and D here. I'm going to go through all of these, okay? And obviously you see the answer because it's in red. I have the answer, okay? One of these is not possible, and the one that is not possible is item A. I'm going to use logic here. Remember, independent means no influence. Mutually exclusive means can't happen at the same time. Can't. Mutually exclusive is a double negative. Can't happen at the same time. Okay? All right. So if 2 events are independent, I'm sorry, if two events are mutually exclusive, they become dependent. This example I always give is, let's say I have a really bad breakup with my girlfriend, okay? And we become mutually exclusive, meaning I don't want to see her, she doesn't want to see me. We have become dependent because if she goes to a party, I can't go. I'm dependent. If I want to go to the beach, tower number 44 at Newport, she can't go. Because when you are mutually exclusive, when you can't happen at the same time, you are dependent on one another. So this is actually not possible. So if you're ever asked a question, which one's not possible, the answer is going to be A. All right, item B, independent and not mutually exclusive. Not mutually exclusive is your double negative. I think I misspoke that earlier. It's your double negative. That means can't happen at the same time. Can't not happen. So it does happen. Now, a good example of this one is flipping a coin and getting heads, or rolling a dice and getting a 4. Okay, so you got, if you're trying to get heads in a 4, here's your sample space. Heads 1, heads 2, heads 3, heads 4, heads 5, heads 6, tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. All right. Now, is a head flipping a coin and getting heads and rolling a dice? Are those independent events? Of course they are. A coin and a dice have nothing to do with each other. So this is, got that. Now, and then not mutually exclusive means can't happen at the same time. No. They can. They can. Heads and a 4. Heads and a 4 actually happen 1/12 of the time. So these are independent events that that can happen at the same time. So, and in this case, what we're talking about is survival and gender and survival. Are gender independent? Yeah. But can you be a male and die? You sure can. So B is not the one either. Okay. Now, dependent and mutually exclusive. Dependent and mutually exclusive. Erase this real quick. Okay. We can go into that more later, but certain things are dependent, but they can't happen at the same time. That does happen. Okay. The answer to item D is, or this question K, is D. Dependent and not mutually exclusive. We've already established that gender and survival were dependent events. And you can be a female and die. Okay. All right. So remember, not mutually exclusive means can happen at the same time. That's a double negative. I think I misspoke earlier, about 5 minutes ago on that. Anyhow, that is chapter 5, day 6. If we got to clean up a couple of these questions, no problem at all. All right. Thanks a lot. Take care.